It seems that Eduardo has a technical problem.
Yeah, we should go move along. So Professor Eduardo was going to present what the Center of Physics in Porto does, what these different research areas. But I believe we can move on to António Antunes' talk. Antonio, you should be now able to share your screen.
Let me give it a try. You can hear me, right?
Yeah, perfectly.
Cool.
Good, good. I can see your screen.
And you can see my presentation, right?
We can.
Okay,
go ahead.
Great.
Thank you.
So, okay. So thanks everyone. Thanks to PLANCKS for inviting Centro de Física to speak here. And my name is António Antunes. I'm a student at the Theoretical Center of Physics in the University of Porto. My supervisor is Miguel Costa, who wrote one of the problems, or helped writing one of the problems. And today I'm going to tell you about how to learn about quantum gravity by studying magnets. And already this kind of points to the diversity in Centro de Física do Porto, to the different topics in theoretical physics that we cover. So for those of you who saw João Penedonis' talk this morning, this might look a bit familiar, but maybe that helps. So let's go ahead. So first, let me start from a simple phenomenology of the ferromagnetic phase transition. So in many materials, this is some phenomenon that is often observed, that let's model a magnetic material by a lattice with a bunch of spins that can either point up, which I represent as orange, or down, that I represent as blue. And at high temperatures, there is no particular orientation of the spins globally, so the net magnetization is typically zero. And at low temperatures, the spins can align collectively, say, and there is an overall magnetization that in this case can point in two directions. This is called the ferromagnetic phase. And if we plot this diagram, let's say the overall magnetization as a function of the temperature, we can represent this more quantitatively. So at high temperatures, the net magnetization is zero, but then there's a special temperature called the Curie temperature, at which the overall net magnetization is not zero anymore, it turns up, and then it can take some positive or negative value. And what's interesting for us is that at this critical temperature, the net magnetization grows with a power law to the distance of the critical temperature, and this it's called a critical exponent beta, has some particular value for this type of magnets. But what's important is that there's a power law here. And why are power laws important? Because they're related to critical behavior and second order phase transitions. So another power law that can show up when we study this type of magnets is, say, when we consider the specific heat of the material as a function of the temperature. It turns out that at the critical temperature, it diverges with a specific power law that I'll now call alpha, with an exponent that I'll call alpha. So it just so happens that at the critical temperature, many types of systems have this type of power law behavior, and the exponents actually coincide very often between different types of systems. For example, the critical point of the water vapor to liquid water phase transition has the same critical exponents as the uniaxial magnets that I've been describing, which might seem quite surprising. And the idea that critical systems have the same critical exponents, or at least fall into some categories, is the idea that there is universality, and these groups are called the universality classes. And what's the reason behind all this mystery that different systems turn out to have the same behavior at the critical temperature? An underlying principle is so-called scale invariance. And to understand scale invariance, we'll need to zoom out a little bit. So we need to look a bit far away from our lattice and see how our system looks like. So at high temperatures, we have the paramagnetic phase, where the spins are more or less randomly ordered. And when we zoom out, we just see a big mass that is essentially a random distribution of spins. But at low temperatures, we will see sort of when we zoom out, we see a homogeneous type of distribution with maybe some small clusters of the opposite spin. However, and what's more remarkable is that right at the critical temperature, when we tune, we find that when we zoom out, there are clusters of different sizes of all types of spins. And what's interesting about having clusters of different sizes is that when we zoom out, the system looks essentially identical. So it dynamically acquires scale invariance at the critical point. So it doesn't matter how far we look at it, it looks the same. That's why it's scale invariant. So my analysis so far has been global, and a global analysis of a system is what we call thermodynamics. And to be more specific, let me give just one more observable, which is the average energy density at a fixed temperature T. What essentially happens in this type of critical behavior, which is called the second order phase transition, is that we have, say, some average energy in the low temperature phase, some other energy at the high temperature phase, and when we connect, the derivative blows up. So the slope is vertical. And that's why it's called the second order phase transition, because the derivative of the energy density is discontinuous. Okay, but what can we know more about the system? We can know more by looking locally. And a local analysis of the system is what we call correlations or correlation functions. So let's study energy fluctuations of the system. By that, I mean, let's study the energy at a given site of the lattice and subtract out the average. Well, of course, the expectation value of a fluctuation is 0. That's what an average means. But we can ask, what's the average of the product of two fluctuations at two different points in the lattice? So basically, how does the energy fluctuation propagate in the system at a given temperature? And it turns out that to study this theoretically, we can use symmetries. And a very interesting region of the phase space to use symmetries is near the critical point. Why? Because when we zoom out near the critical point, there are emergent symmetries that the lattice hides. So in particular, translations and rotations emerge, continuous translations and rotations, only a discrete form of it survives in the pure lattice. And furthermore, at exactly the critical temperature, there are some bonus symmetries, in particular, these rescalings that we mentioned of zooming out, the system looks the same, and also a spectacular miraculous symmetry called special conformal transformations, which together form what we call the conformal transformations of the Euclidean space. And there is no really very good general theoretical argument to see why we have these special conformal transformations. And I won't even explain very much what they are, but let's just say that they are extra symmetries of our system at the critical temperature. And what are symmetries good for? They're good because they tell us how correlation functions can behave. So the correlation function of 2 points that we were mentioning before clearly must be a function of the distance by translation invariance, and it must be a function of the norm by rotational invariance. But scale invariance is very strong, and that it fixes this 2-point function to be a power law, just a power of the distance. And this exponent is called the scaling dimension of this operator. We call it these local objects operators. And so the scaling dimension is very important in defining the physics of the model because it tells us how far these fluctuations propagate. And then we can go further. We can study correlations at 3 separate points. What happens if the energy density fluctuates at 3 points? And it turns out that this conformal symmetry, that is like this enhancement of the scaling invariance, completely fixes the 3-point correlation functions up to an overall coefficient that we'll call the OP coefficients. So these are just a bunch of numbers, these deltas and these C's, but they are very important and we call them the CFT data. They are a set of numbers that will qualify this conformal local theory that we are studying of the correlations of the critical system. And one thing that I should mention is that, of course, the energy density is not the only local observable. Of course, I can study general local observables. I could ask what is the local magnetization, for example. So I put a label I to mention the different observables that I'm studying. And now, for the final magic trick, we'll look at 4-point correlation functions. So the number of points keeps growing, and complexity will also grow. But this time is very different, because now, when I study a correlation function of 4 local fields, it happens that it's not completely fixed. The symmetry conformal invariance does not fix it. And now there are some interesting variables called the cross ratios that depend on the 4 points like this. These are just the distances between the points squared. And these ratios are conformal invariant. That means that the symmetry does not determine what this function is. And so it might feel a bit stuck. But fortunately, the scale invariance of the system allows us to use something which is called the operator product expansion, which essentially means that local fluctuations, which are close to each other, can be expanded as a single fluctuation. This essentially means that if I have 2 points and I put them in a ball that is farther away from everyone else, I can just replace this by a single point in the middle. This makes sense because they're scale invariant. So if I pull the points far away, they essentially look like a single point. And this technology is incredible because it allows us to determine this in principle dynamical correlation function in terms of these numbers, the C's that we studied before for the 3 points and the deltas that appear in the 2-point correlation function in the propagation. So I wrote this function G here. It's not very important. It's just important to know that it's a known function, as where before this F is completely generic. We don't know what it is. So now we have a basis that in terms of this dynamical data, this critical exponents and these 3-point coefficients, fixes for us the 4-point function. And why is this useful? Because it's the way we did this by making points close together, let's say pairing points 1 and 2 and points 3 and 4, and using this operator product expansion, breaks the permutation symmetry of the correlation function. And we can demand that it is restored by doing a similar expansion, but instead pairing points 3 and 2, 1 and 4. So this gives us two sums in terms of the CFT data, these dimensions and the OP coefficients, in two possible channels. And in terms of diagrams, I can just say, okay, I connect 1 and 2, and I have this operator K that is in these spaces, and 3 and 4. So I can do these two pairings. And similarly, I can do it for points 1 and 4 and 2 and 3. And this equation is highly non-trivial because there are in principle an infinite number of local fields whose dimensions I don't know, and I also don't know their coefficients. But there is also an infinite number of equations because this is true for any location of the 4 points. So this is an infinite number of unknowns and an infinite number of equations. And we might wonder if there are solutions to this. And it turns out that there are, and that they're very physically interesting. So one way to analyze the solutions is analytically in some kinematic regimes where the points are in some specific locations. But I'll focus more on the idea of analyzing this problem numerically. And the way to treat this problem numerically is to choose specific positions and then do a Taylor series around those particular positions. And then we basically are truncating this equation to a finite, infinite number of equations to a finite number. And it turns out that we can use this to severely constrain the dynamical numbers of the critical theory. For example, for the 3D easing model, that's a very famous lattice model that many of you might have heard about. It describes uniaxial magnets in 3D. It just so happens that the critical exponents for the local magnetization, so for the spin operator, and for the local energy operator, are so restricted that they form a little island in this space of parameters of the theory. And in fact, this technique is better than any other technique, including simulations that directly attack this model. So these arguments that I gave just used conformal invariance. They just use that the theory is at the critical point. And they give better predictions than any specific simulation that actually attacks this number. And an interesting comment is that the fact that these solutions are so tight and so restricted is a posteriori justification to universality. The fact that these critical systems are so constrained and there are so few solutions sort of justifies why these critical numbers are the same for many different systems. They have no other choice. So let me make justice to my title. So this is the last slide. So I was talking about critical ferromagnets, and now let me jump to quantum gravity. Why did I mention quantum gravity? The reason is that there's a very special kind of space called an anti-de Sitter space. It's essentially a saddle of a horse, so it has negative curvature everywhere. And we can study quantum gravity in this space. And the reason why it's easier to study quantum gravity in this space rather than our usual space is that anti-de Sitter space is essentially a box. But it's a box that looks the same everywhere, so it's not your ordinary kind of box. And furthermore, it's a box that is scale invariant at the boundary. So if this sounds familiar, it's good because we're studying scale invariant systems. And it turns out that quantum gravity in this special box called anti-de Sitter space, so quantum black holes and scattering in quantum gravity, all of these types of complicated questions can be asked, and they are related to conformal invariant systems. In particular, scattering in quantum gravity in this special box is actually dual to the 4-point correlation functions that we were discussing before in conformal field theories. So remarkably, we can use this extended knowledge of conformal field theory to sort of define what quantum gravity is. And quantum gravity is essentially a unifying theory of everything that we want to study in nature at the most fundamental level. And it's very interesting to have a handle on it by describing it as a type of theory that we can use to study magnets. So that's how we go from magnets to quantum gravity. So let me conclude by showing you this quote of a very famous physicist, Sasha Poliakov, that once said that I wanted to learn about elementary particles by studying boiling water. So here we did sort of the same. We tried to learn about quantum gravity by studying magnets. So thanks a lot. And here's my email if you guys have any questions and want to ask them with more time. So thanks a lot.
Thank you, Antonio. I was about to ask, because we are really running late, if you can also write your email on the chat so that if someone has questions, they can, if someone has any questions, they can email you. So I think now we have Professor Eduardo will be able to share the screen.
Yep.
Thank you, Antonio, once again.
Thank you.
Okay, can you see my screen?
Yeah, perfect. Go ahead.
Okay, greetings everyone. Thank you, Sophia, and thanks to the organization of PLANCKS 2021 for inviting me and for inviting the Centro de Física do Porto. So I'm here trying to let you know a little bit about this research center here at the University of Porto. So in English, it would be the Physics Center of Porto. Actually, this is a unit, one of the units of a larger research center called the Physics Center of the University of Minho and University of Porto. So it's a research unit that brings together researchers in both universities doing research in physics in different areas of physics. This unit in particular, this Physics Center of Porto, is about theoretical physics. So here you see our the building where part of us live, and the city of Porto that you would probably be visiting if the circumstances were a little bit different. So we are a small unit, so 17 members with PhD right now, and you have several students. Actually, the working force, of course, are the students, as you know. And you have just heard António, which is one of our PhD students, and it was not planned, but I'm very glad that António spoke before myself, because I think he beautifully showed that it's a good idea that we have a center in theoretical physics that tries to understand the theoretical phenomena in physics, which can go from, as I will tell you in a moment, from quantum matter to high energy physics, cosmology, quantum condensates. The truth is that you can find the common language. We can learn from each other, and it's very fruitful that we have this kind of research unit where different aspects of theoretical physics can live together. So these are the master students. This number fluctuates a lot. So this year we have 3, sometimes more, sometimes less. But that's the idea. So we are a theory group, and of course, as you know, we need paper and pencil. But nowadays we actually use a lot also the computer. When we say computer, we say computing clusters, and this grid FEUP is actually our own cluster. So it's the computing facilities that we have at the University of Porto that we can use as far as they are available, of course. But this is reasonable, but of course it's not very big. When we need better facilities, we apply for computing time in other research centers, and we have right now a project running in this Beijing Computational Science Research Center. So they have one of those supercomputers with a lot of cores, and we have also very often some national projects that can also apply, and we do. So we are also intensive users of high performance computing facilities. So I will tell you briefly a few things about our main research lines. So I divided into 3 parts: so quantum matter, high energy physics, and cosmology and nonlinear physics. But again, let me show you António, because he beautifully has shown that indeed this is just a way of trying to put the visions in something that can actually bring into a common language, and for sure quantum matter and high energy physics have a lot in common. So just to tell you a little bit about quantum matter, I would say that we do research in new quantum materials, new quantum behavior, and we have also these advanced computing research projects. So for new quantum materials, I'll give you this example, which is not actually quite new. So graphene, I'm sure that all of you have heard about graphene, but I'm just pointing here graphene again. So this is 2004 or so, because so in our research unit we started working in graphene right away. So in 2005 and 6, you can see papers, interesting and I would say important papers about graphene with our research unit in the address. But recently there was I would say a revival of graphene with something called twisted bilayer graphene, and a whole new area called twistronics, and so this is what you would see if you look at 2 single graphene layers that are a little bit twisted, so a little bit rotated with respect to each other. So there is this long wavelength modulation called Moiré pattern, and it gives rise to very interesting and fascinating physics, which you cannot see in single layer graphene. So this is the spectrum of single layer graphene, and here you can actually find, for instance, superconductivity and strongly correlated phases. And I'm sure all of you will, if you have not yet, will heard about this twisted bilayer graphene in the future. New quantum behaviors, so topological matter is something that we now also explore in our research unit. And for instance, nonlinear optical response. So here again, this is nonlinear optical response of graphene. So you see here the linear spectrum again, and this is just an example. You see that, for instance, the third order harmonic is actually as an intensity much higher than the linear or the second order response. And finally, so one of the projects and outcomes, I'd say, of this advanced computing research that we have in this center is this quantum kite. So this is a high performance quantum transport software. So it's free. I mean, you can actually try to download and to do some calculations with it. What is very impressive, the number is very impressive in this software, is the fact that you can actually simulate systems with 10 billion atoms, which is actually very, very interesting. But I'll let João Pedro Pires after me and tell you a little bit more about quantum matter. So the other field, high energy physics and cosmology. So we have still, and as you know, dark energy and dark matter as one of the mysteries, and we have researchers working on this. The theory of gravity, extensions and alternatives, quantum gravity, of course, and if we talk about quantum gravity, you of course will end up with black hole physics. But I'll let Professor Orfeu Bertolami tell you a little bit more about this. So a new and a recent trend is the gravitational waves, and in this unit we are trying to apply deep learning in gravitational waves. So as you know, so gravitational waves, they are detected using this interferometry facilities. And the problem is how to actually detect what is the gravitational wave signal, or to distinguish it from the background noise. And so we try to apply deep learning techniques to this, and the results are actually very, very encouraging, where you can actually try infer the mass and the distance and the speed. Finally, nonlinear physics, and I believe I'm running out of time. The nonlinear physics that is actually being done here in this research center has a lot to do with the Bose-Einstein condensates, while I have here Bose and Einstein. But the new, and these are examples using optical lattices. But the new condensates, very interesting condensates, are these polarity condensates, because so you can do a lot of more things with temperatures close to room temperature, and this is also very interesting and fascinating. Okay, so thank you very much. I'll leave you with Orfeu and with João, Pires, to let you know a little bit more about all this stuff.
Thank you, Professor. As we said, let's move on to João Pires' talk. João, are you there?
Yes, I am. Let me
Can
just
you share your screen?
Yeah.
Thank you.
Okay. Can you see my presentation in full screen?
Yeah, perfect. Go ahead.
Okay. First of all, thank you very much for the invitation to talk here. So as Eduardo told you, I am a member of Centro de Física, and in particular, I work within the condensed matter theory group, which I present here. So we have currently three senior members, led by Professor João Lopes dos Santos, and Eduardo himself, and also João Viana Lopes. Then we have other students that are on the PhD, either in the beginning or in the end. One of them, which is Niaz Alihan, which has already finished his degree, but many of the work that I will present had his participation, so I decided to put him here. So there is myself and Simão João, and then we also have four other currently PhD students, which also work in condensed matter theory, but in an area that is a little bit departed from what I'm going to talk about. And we have also other project non-PhD students, which I won't refer here because they would occupy too much space in the slide, but they are as important as we are. So in this group, the main topic is essentially the physics of electrons in crystals. So as most of you must know, in condensed matter, if we are talking about solids and in particular electrical properties of solids, we are always dealing with crystals, or at least approximately crystalline materials. And in this case, we can see the electrons as quantum particles that are traveling across a potential that is periodic in space. It has a certain periodicity which is determined by the underlying lattice. So we have a very concrete problem of quantum mechanics to solve then. We have a non-relativistic particle that travels through a potential that is periodic. And as it turns out, this problem have been solved for quite some time, since the 1920s actually, that we know the precise form of the wave functions of these electrons, and this is given by Bloch's theorem. So we have a wave function that is essentially a plane wave that is modulated by a periodic function u that depends on k, on the wave vector. So the wave functions are like this, and the interesting thing is that they are not precisely plane waves, but they are like plane waves, which means that if you have a perfect crystal, your electrons will behave as if they were perfectly delocalized waves. And so this is the reason why you can think of electrons in a metal, for example, as a gas of independent particles, is one of the reasons. And and those theories work very well when compared to data that are obtained in experiments. However, we also know that reality is always much more complex than what we theoreticians can simulate. So we actually don't have perfect crystals. We have something that always looks something like this. So you can have a crystal, and then at certain places you should have an atom there and you don't have anything, or you can have extra atoms, or you can have deformations of the lattice itself. So in this case, the basic quantum mechanical problem that we need to solve doesn't have a solution in general. Okay, so we need to take this system as disordered in the sense that it has some kind of randomness in the Hamiltonian itself, and deal with the physics that way. And this is one of the things that people have been doing, and one of the research areas, the main research areas, I would say, of our group. So first of all, why is disorder interesting? Because we can think of disorder as a complex array of scatterers in space that are randomly placed, and where our block waves, our plane waves, are scattered. So if they scatter in a random fashion, then they can come back to the same place, since they are matter waves, and in that place they will interfere with themselves. So this can change dramatically the nature of the quantum states that we are talking about. And here you have an example that was obtained for a disordered sample, in this case one-dimensional, and you look at the wave function in space and you see that it doesn't look anything like a delocalized wave. It is localized near a point that is a random point, but it's a point in space. This is what we call spatial localization, and it has been known since the 50s, and it actually gave a Nobel Prize to Phil Anderson in the 70s as well. But there are other important consequences of these interference effects in random media, and I give you some examples here. For instance, the quantized Hall effect, which was also a subject that was awarded a Nobel Prize. We also have what we call universal fluctuations of the magnetoresistance, so sample-specific fluctuations. And we have, for example, strange statistics of the conductance if you look at different samples, different disordered samples. So there are many other effects like these, which have been studied since the 1960s, 1970s up until now, and there are many more to be discovered. So we have been doing some work. We have been doing some work in this area as well. And I will give you here a kind of a summary of the main results that we have obtained in disordered electrons for the past, since 2018. Okay, so for the past 2-3 years. So first of all, we looked at what happens when electrons are propagating through a random medium, but it's not completely random. So you have some kind of correlation, actually long-range correlation in the potential. In that case, one of the first things that we looked for was, okay, how do the eigenstates of these electrons look like? And for doing that, this is an equivalent question of asking how do the plane waves so how different are our eigenstates from a perfect plane wave? And this is encapsulated in one quantity which is called the spectral function. And doing numerical calculations, which is always the way to go, or almost always the way to go in analyzing these systems, we obtained a very non-trivial behavior, which is non-perturbative, and it's shown here, which was published in 2019. And after that, we went and analyzed what are the consequences that this kind of correlated disorder have in transport properties of the system. And one thing that we obtained was that there was actually a phase transition happening, a trivial one actually, but there was a phase transition happening in this system as a function of a parameter for the correlator of this disorder. Another thing that you can do is to study transport, in particular time-dependent transport of electrons across a random medium. For example, imagine that you have a system like this, which has a disordered sample in the middle, and then it is connected to leads, which will mimic perfect electrical contacts. And then you turn on a potential like this, which will obviously drive the electrons across the sample. So now you measure the current, and when you measure the current, what you discover, and what we have discovered, is that you get a transient state in which the current is constant. And this is basically a quasi-stationary regime in which the electrons move coherently across the sample without, almost without any, or without any dephasing. So they are scattered, but they achieve a balance in which you have a continuous current being carried through the sample. Okay, but there are many other effects. For example, you can look at the effects of disorder in optical responsive materials, and we have done this, not me particularly, but the people that are here in the slide. And here you have an example which was done for graphene with disorder, in this case gapped graphene, so graphene with a spectral gap. We also, as Eduardo mentioned, we have also participated in the development and release of a wide purpose open source software that is able to calculate almost any electronic property in a disordered lattice, which is called the quantum kite. And here you have an example where you calculate the spectral density of states in twisted bilayer graphene, which is, as you know, a very interesting system these days. So you can download and use yourself this software if you want. And importantly, this software also provided us with unprecedented opportunities to study real-life systems with interesting disorder-induced physics. And here I have two examples where we have done that. So we have used the technology, amongst other things, but we have used the technology that was developed in KITE to study systems that are very interesting today. For example, Eduardo, together with his collaborators in CFP in Lisbon, studied what happens when you have a disordered loop vial semi-metal, and he saw that there is actually there are actually two critical points where the nature of the electronic states change due to disorder, to an increase in disorder. And me and also my PhD supervisors, we analyzed a rather different setup where you have a nodal point semi-metal. And in that case, we saw that the introduction of disorder, of a special kind of disorder, actually makes it unstable, so makes the semi-metallic phase unstable and turns it into a metal very quickly. And we also published this very, very recently. So you have here some of the references that I have shown you. And thank you for your attention. And if you are interested in working in this area and talking to us, please contact me.
Thank you, João. I don't think we have time for questions. I ask you that you please write your email on the chat so that if someone has a question, please do email João. With this, I ask Professor Orfeu if you can share your screen and start presenting. We can see your screen, but we cannot hear you yet. Professor Orfeu?
Yes.
Now I can hear you. Yeah?
Can you hear me?
Now I can, yeah. But we cannot see you if you...
Oh, you cannot see me. Okay. What's wrong? Let me go back. Let me go back. Okay, I think, can you see me now?
Yes, perfect.
Okay.
Go ahead.
I'm sorry. Thank you very much for the invitation. Thank you very much for the previous talks. It has been great to hear about the colleagues from my center. So I'm talking about some of the fundamental physics developed in our center, and likewise Antonio, who said that, mentioned Polyakov that want to do quantum gravity looking for boiling water. And you'll see in the end that you try to understand the climate change through the boiling of water and from the freezing of water. Well, we know you are in the most western part of Europe, you are in Porto, north of Portugal, and while we speak, most of the European leaders are discussing the social chart of Europe a few hundred meters actually from where I'm sitting. And I hope they have as many as bright ideas as the ones I've been hearing sitting in this afternoon here. So these are the partial list of the things I'm interested in: dark matter, dark energy, the relationship between both, alternative theory of gravity, and I'll tell you something about this model, the one on which gravity and matter are coupled minimally. And more recently, I'm interested in phase transitions related with the Earth system. This allows us to compute trajectories in the Earth system, and in particular to understand the climate change. I have many slides, so I have to be very quick. So, as you know, the universe is dominated by dark components about which we know very little. Dark matter, for instance, is seen through the rotation curves of galaxies. What we want to explain is how is it a particle can be long-living and feel that that energy density that's missing. So you have a list of candidates, and I'm going to talk about a candidate I'm very keen on, namely light scalar field. I've been saying that for quite some time, for more than 20 years ago, and in this research here, phi is a scalar field, and the novelty here is to couple it with Higgs field. The possibility is that you can produce this particle in accelerator once you have a factor of Higgs field. When you propose it was not available, but as you know, LHC is a factor of Higgs particles, and somehow we have already the way of saying something, or at least to put bounds on this particle. It turns out that the modern realizations of that, this was done with a student of ours, in CFP, Katarina Cosmi, a modern version of that turns out that it requires that this particle is very light, and it admits several realizations. Another realization, for instance, is that this particle acquires its mass through the very Higgs mechanism that gives mass to all particles in the standard model. And if so, this particle, in fact, can be somewhat heavier and have, for instance, a keV mass. And this can explain, for instance, some lines that are observed in some galaxies. It fulfills all the requirements to be a good candidate for dark matter. And unfortunately, it's very hard to see experimentally, but it's not out of a question in the near future. So this is an example of the research that's being done in our center. So let's say something about dark energy. As you know, this is to do with the accelerated expansion of the universe, and there are several ideas about it. One that I'm very keen on is this one which is synthesized by this equation of state, the so-called generalized Chaplygin gas equation of state. We have shown long ago that this equation of state allows us to have very nice properties. In particular, it allows that in the early universe, you have a dark matter type of behavior, and the late universe, you have a cosmological constant type or a dark energy type behavior. So this is a sort of a unified model of dark energy and dark matter, and we have shown that this is consistent with all the phenomenology of cosmology. Well, if you are not keen on the idea of dark matter and dark energy, so you have to give up general relativity. And as you know, nature can be very tricky, and possibly you have to work on an alternative theory of gravity. We've been hearing about quantum gravity. This is the high energy behavior of these theories. But when you test things in cosmology, we are talking about the infrared limit. And one of the ideas is to generalize relativity at this limit. There are many other ideas, but one of them is in which you introduce, instead of the linear curvature term of general relativity, you allow it to be a more complicated function. And in fact, you couple matter with another function in a non-linear way. So this leads to more complex equations of motion and a very interesting behavior, which allows you to explain certain properties of galaxies and of cosmology. For instance, you can get for free the so-called Tully-Fisher law, which relates the luminosity of spiral galaxies with their quartic velocity as an example of these properties, and many other things. Of course, if you propose something different than general relativity, you have to go through the whole phenomenology and say that this is consistent with everything else that you have seen. So we've been working in the last few years with this theory and been showing that, well, it's consistent with the stellar equilibrium, it's consistent with microwave background radiation, it's consistent with, it admits black hole solutions, etc., etc., etc. So this is a very large class of research, and many people have contributed to the phenomenology and the calculations that allow us to say that this theory is still consistent with observations. Well, let me go now to the last part. As I said, the time is very short. So, you know, we live in Anthropocene. This is the geological era on which man dominates the whole planet. This is started more or less in the 1950s of last century, and as you know, man is so overwhelming on our planet that we are affecting its climate. This is the blue picture is how the climate changed throughout the history, and the last 2,100 years, the weather has been very, very stable. This is area is called Holocene, but the human activities, in particular, the concentration of dioxide carbon in the atmosphere has been changing that. So the Anthropocene is in fact is a host of very complex problems, and climate change being just one of them. And in particular, we've been observing that the temperature is rising unequivocally, and the only explanation for that is the rise in the concentration of greenhouse gases produced by man. What's going to happen in the end of the century, we don't know, but estimates are appalling. They predict that the temperature can vary from 2.5 degrees to 4 degrees, or 5 degrees. This will be disruptive to our civilization. So how do you understand that? Well, there are computer models of the weather, but of course, if you have an idea to obtain the so-called Anthropocene equation, or how the system evolves, it's very helpful. So the idea here was exactly what António was telling us. The idea is to consider these variations in the climate of the Earth very much like the phase transitions of water. So, and there is a very well-known theory that attacks these problems in a single go, the so-called Landau-Ginzburg theory, on which you have an order parameter, and you can write from this order parameter the free energy. That was the idea. So from this free energy, you can write down this evolution equation. So this is a typical example of how a material behaves under different temperatures. And what you are saying is that, well, there's different ups and downs in the history of the Earth system that in fact correspond to minima in this diagram here. how do you model human activity? Very much like you do in material physics. You introduce an external field, and here the external field is the human action. And so this is destabilize the system. Well, sorry, I'm going the wrong way. This is stabilize the system, and that's exactly what we have shown. We have shown that indeed these human activities actually lead the system through an intermediate phase that we call Anthropocene, from the Holocene to a new minima on which the temperature is higher, and that's problematic, as I have mentioned. You see these people here that work on these matters from a weather, from a Earth system point of view. They mentioned that the interaction of the major ecosystems of the planet suggests that we are really going into this hot phase. Now, from our approach, you can show that this is indeed mathematically what happens from that free energy that we have proposed to start with. So we can also show that this is an accounting system. This provides a physical way of measuring what man is doing on the system, how quantitatively human activities is driving away the system from the stable Holocene phase. This is done from this modeling of the human activities. And we have shown in that paper that, for instance, you can connect many of these areas, for instance, with these interaction terms between climate change and, for instance, ocean acidification. This allows us to, for instance, to propose some more effective ways to mitigate the problem. And one of these ones is the idea that should stimulate local communities to restore ecosystems. And in order to allow them to do that, you should invent a new coin, a new crypto coin, call it planetary boundary coins, on which all communities would pay a local community that restored the ecosystem through this PB coin. If this PB coin can be converted in real money, so you can buy seeds, you can buy manpower, you can buy expertise to restore an ecosystem. The idea is to stimulate the local communities to go through these digital contracts so that we can restore the ecosystem. There are many similarities between what's going on in the pandemic and what is going to happen in the near future with climate change. Climate change will be a succession of disasters that will put us at home for quite some time, with the difficulty that probably there will be no water and no food available to everyone. So you have to take care of that as soon as possible. So after that, I can thank you for your attention.
Thank you so much, Professor Orfeu. We have a question on the chat. That's the only one we have time for. So Sydney, let me see. You can unmute yourself.
Yes, let me see if I can read that.
Well, I can also read it. So the question is, these alternative gravity models like FR still need to couple to the GR in some way, and even with Newtonian gravity. Is this coupling trivial for this series, or it needs some work and restriction in the FR form?
Sorry, can you repeat it again?
It's also on the chat, but these alternative gravity models like FR still need to couple to the GR in some way, and even with Newtonian gravity. Is this coupling trivial for this series, or it needs some work and restrictions in the FR form?
Wow. The theories I have proposed are, let's go back. The theories I have proposed generalize okay. So you see, F of R theories are well-established theories. Some of them displaying quite well the phenomenology, but there are some holes in it. And that's why we have proposed an extension. This extension has this no-minimal coupling. This no-minimal coupling allows to do other things, for instance, mimicking. It's a new property of this theory. So it means that you can trade, for instance, the distribution of dark matter, which is not possible in f of r theories, for an f of 2 of r modeling. So this theory has some more flexibility and has many new properties. For instance, there is a violation of the conservation of the energy momentum tensor in these theories. This doesn't occur in f of r theories, and this property, for instance, is useful for instance, the very early universe. So. Yes, this theory is more general than general relativity, of course, and it has a much richer phenomenology. So that's the only thing I can say. So far, it looks good. We haven't seen any contradiction. And as I mentioned, you see, you have been testing this theory in many playgrounds, and it's been working so far. So that's the only thing I can tell you.
Maybe I can ask you, Professor, if you want, you can write your email on the chat if there are follow-up questions. And Sydney said, thank you, love the presentation.
Thank you.